Hello and welcome to Chapter 3. So in Chapter 3, we discuss some concepts of energy and also introduce the first law of thermodynamics. Remember, as we go through our lecture note types of materials as if we were in class, my assumption is that you've read the textbook in detail, and then also, if this were a normal class, much or most of class time would be spent working through problems. Right? So here, my goal is just to try and highlight some important concepts from the chapter. Okay, so here begins chapter 3, and in this first set of notes, we'll mainly just talk about heat, work, and very briefly internal energy. Okay. All right, so now energy versus work. Right, so energy is storable. Okay, so it's a state function. It remains in a system as long as the state of that system is preserved. So if I have a ball and I put it up the top of the mountain, right, the potential energy of that ball is going to remain the same so long as I don't knock the ball, say, off the hill. Right? As long as it remains on top of the hill, right, its potential energy is unchanged. Right? It's the same. It's stored energy. Okay? It's a state function in that case because if my ball is on top of the hill, so if I say, here's the coordinates of my ball, then the potential energy of that ball is known. All right? So it's a state function. It's storable. If I were to take a ball from the bottom of the hill and put it at the top of my hill, right, I could calculate the potential energy at the bottom of the hill based on its coordinates. I could calculate the potential energy at the top of the hill based on its coordinates. If I wanted the difference in energy, I could take the difference between those two values. Right? Doesn't matter how I get from the bottom of the hill to the top of the hill, the difference in energy would be exactly the same. Work, on the other hand, is energy in transit. So it's not a storable quantity. And so how you can think about work is I've got my ball at the bottom of the hill. I have my ball at the top of my hill. Again, the energy at the bottom of top is only a function of the coordinates. So if I wanted to compute the change in energy of that ball, I could just take the difference between those two potential energies at the top and bottom of the hill. What work would be is say, the work it takes to take the ball, right? Work is going to have the same units of energy, but it'd be how I take the ball from the bottom of the hill to the top of my hill. Okay. Now, work as compared to energy is not a state function. It's going to be a path function. So the amount of work or energy it takes to get from the bottom of the hill to the top of the hill is going to be dependent on how I go about said path. Am I going to circle around the mountain and go up the opposite side, which maybe has less of a steep slope? You could think of all different sorts of scenarios. Okay, so work, right, is that energy that takes the ball from the bottom of the hill to the top of the hill. It's going to be dependent on how I get from the bottom to the top. Right, it's going to be path dependent. Okay, so energy is a storable quantity. It's a state function. Work is not a storable quantity. It's essentially energy in transit. And it's going to be dependent on how I get from my initial to my final state. Okay. The sign convention that we're going to adopt in this class is that if work is done on our system, then that's going to be positive. If work is done by our system, it's negative. All right, and so here, again, it's just a simple example of that ball. Okay, if I think in terms of potential energy, in this first picture, right, I have a ball at the bottom of, say, some step. Okay, the potential energy of that ball is fixed by the coordinates, right, of the ball. All right, so in case of potential energy, as long as I know its height above sea level, all right, then I can readily compute its potential energy. If I have a ball at the top of that step, same thing. Its potential energy is dictated solely by its coordinates. Okay. If I wanted to calculate the difference in energy between the state B and the state A, I can just take the difference in those two potential energies. Okay. Work, right, is the energy that I'm using to take my ball from state A to state B. Okay. So work is energy in energy transfer, energy in transient. And so it's not storable like potential energy is here, right? And then more importantly, it's a path function. So it's going to be dependent on how I go about taking my ball from state A to state B. Okay. So just a picture of some examples of work from the book. All right. So here's a windmill. So windmill, is an example of shaft work, right? So I'm twirling my propeller. All right, so here's an example of shaft work. We're also going to have two. We're mainly going to be focused in PV boundary work, right? And keep in mind, we said the first law of thermodynamics has its origins in the Industrial Revolution in the development of the steam engine, right? So the most common scenario is thinking about, say, a piston cylinder apparatus, where I have the expansion and contraction of a fluid, which is going to move a boundary, say, up and down, right? A piston head. Right, and so that'll perform work, right, against my surroundings as the piston head goes up, and my surroundings will perform work on my system as the head goes down. So we'll refer to that as PV boundary work, or just here in general, we have the general expansion and contraction of a system, which would perform work on the surroundings, and the surroundings would perform work on it. Okay, so as we think about this PV boundary work, so most of the problems, or a lot of the problems we'll solve, will involve reversible PV boundary work. And so the general idea here is, here I have my differential of work. All right, so work, right, as we remember from our physics class, is just force times displacement. All right, force times displacement. So in its differential form here, the differential of work is my force times dx, right? So you could think of this as essentially just your displacement, right? It's a differential change in position. Okay. So this would be, the work associated with some infinitesimally small change in x dx. So work is a force times displacement, or in differential form, assuming this constant force, dw is f times dx. Okay. Now, when we think about PV boundary work, what force are we referring to? Well, we're referring to pressure. Remember, pressure is a force per unit area. So if we have the scenario of a piston head moving up and down of known cross-sectional area, then the force is pressure, which is a force per unit area, times that area. Okay, so my force is my pressure times, say, that cross-sectional area. And if we assume, say, in my piston cylinder, that my area is constant, I could actually take that out and put it into the differential. So what's being done here is, if A is constant, I could bring it out and actually put it in my differential. Right? So if A is constant, it could just as well come out of my differential. The reason for doing that is my cross-sectional area times my displacement gives me the differential change in my volume. All right? If I have some area that's moving some distance, all right, this would correspond to the change in volume. Okay, and so writing it this way, then, force times displacement, I rewrite as pressure times volume. Right, so dW is P dV. Okay. Cool. Now, in order to get our sign convention right, so I have this written just as some external pressure. So based on our sign convention, we said that when our system does work on the surroundings, it's negative. When work is done on my system, it's positive. So if I have my piston cylinder apparatus, if my volume is increasing, right? So if my gas is expanding, right? So the volume increases, that correspond to dV being positive. So if it's expanding, it's doing work on my surroundings, right? I'm expanding, so I'm pushing essentially my surroundings up. Okay, so if expansion corresponds to my system doing work on my surroundings, then need a negative sign in there to make sure I get my sign convention right. All right, so I'll emphasize here, negative, right, PdV. Okay, and maybe I'll get another pen. Negative PdV. All right, and so if I wanted to get the total work, then I would just integrate my differential from my initial state to my final state. So the reversible work would be the negative integral from my initial to final state, PdV. Okay. And so, in general, in this course, if there's any shaft work involved in a problem, all right, we don't have a simple equation that we could just, apply in general. All right, so we'll mainly be looking at problems involving PV boundary work. If we have a problem involving shaft work, there'll have to be details in the problem with regards to how to calculate it. All right, so this is just a picture of work is on a P versus V, say, phase diagram, or P versus V. So if I have a P versus V diagram, right, and so the key here is if I have some initial state here, all right, at volume VA, and then you could read off the corresponding pressure, call it PA, and my final state, all right, has this volume VB at some pressure PB. The work, all right, becomes the area under this curve. Okay, the work is the area under this curve. All right, work is the integral of P dV, so it's the area under this curve. Now, what you do need to be careful about, though, right, is work is a path function. Okay, so I could connect state A to state B in any number of ways. Okay, maybe I have a series of elementary paths in which, I don't know, volume is constant, but I increase pressure. All right, in which case, the work associated with that process would actually be 0. Right, and then I'm going to have some process in which I keep pressure constant and just increase the volume. Right, and so clearly this path here, right, from state A to B is very different. Right, and so key to remember is while work is the area under the curve, okay, that area is going to be sensitive to the path you take from state A to state B. All right, a new concept that'll be introduced here that we kind of mentioned in Chapter 1 is this concept of internal energy. So in Chapter 1, we introduced some molecular concepts. All right, and so namely, we said that molecules move. Right, you looked at an example problem calculating the kinetic energy of molecules in a liquid. And we know that molecules have potential energy due to their intermolecular interactions. So the internal energy is the sum of the molecular kinetic and molecular potential energy of your system. Okay, so internal energy corresponds to the molecular potential and molecular kinetic energy of your system, right? Internal energy, right? Think of it as energy that's stored within the molecules of your system. Okay, your internal energy is going to be symbolized by U, and just like we've talked about or mentioned, potential energy is, you know it from your physics classes, all right? Internal energy is also going to be a state function, right? So it's going to be dependent on the state of my system. Once the state of my system is specified, it is fixed. Okay. All right. Now heat, right? So heat is very similar to work in that heat is energy in transfer. Okay. So heat isn't a storable quantity, right? It's an energy transfer, right? It's an energy associated with a process and taking my state from some initial to some final state. Like work, it is path dependent, and so like work, it's path dependent, it's transient, it's energy in transfer and going from some initial state to some final state. And we also have a sign convention for heat, right? Our sign convention for heat is that heat added to our system is positive. Heat removed from our system is negative. Okay. So again, heat added to our system is positive. Heat removed from our system is negative. All right. I'll see you in the next set of notes.